I'm going to hand over now to Rick and Tom from MyVoice. Rick and Tom are going to talk about the voice of AI, harnessing voice metadata for GenAI solutions. Take it away, guys.
Thank you. Thanks, Davis. It's great to be part of this session today, and thank you, Olga, for organising the event. So, as mentioned, Tom and I are here to tell you a bit about the work that we're doing at MyVoice AI. So we're going to be talking about speech and voice. So speech is it's not just words. In fact, the human voice carries a rich complement of biometric data. This includes our identity, emotional state, and other human attributes. And during this session, we'll explore how foundational and GenAI models can use voice metadata to build more context-driven, intuitive, and personalized features and experiences, and that's on device itself. So we're going to kick off by introducing NanoVoice. That's MyVoice's speaker verification engine. With NanoVoice, voice assistants not only understand what's being said, but also who's speaking. And thanks to tinyML technology, we can run this on ultra low power devices. We have a small footprint, and it's a significant leap forward in silicon-based secure enclaves, and it's applicable to any microphone equipped device. It allows us to identify and speak in real time whilst protecting the user's data. And we see a number of applications of our technology, our speaker verification technology, for both security and personalization, from smart home security to smart TVs and wearables, as well as many others. So NanoVoice operates at the edge, and we're leveraging processors like the Greenwave's GAP9, Sentient NDP120. And I believe Malik from Sentient will be speaking on day 2 of this event. Perhaps, I know we've spoken about it a bit already today, but perhaps, Tom, you could shed some light on why inference at the edge is significantly important, particularly around the realms of voice biometrics.
Yes, so I mean, you've got obvious things that have been covered elsewhere, which is low power consumption to actually run the model. There's latency concerns. So if you're not having to send data and wait for a response, that also makes things a lot more quick. And I think here it's really important is user privacy. People are getting more and more aware of where their data goes. And when you talk about something like voice, it's not like it's personal data, but it's really personal data. It's not your address going somewhere that you don't quite know where it's going, but it's something, you know, much more integral to you. So I think keeping as much sort of data in your hands, in your control, is, it's like of a huge concern for the end user, basically.
Thanks, Tom. And with NanoVoice, we have varying sizes of models depending on the application, and our smallest is around 300,000 parameters. So, Tom, what techniques do you use to downsize large machine language models to from that operate on the cloud to deploy to those models that can be deployed on the edge? And how do you make sure you maintain performance while doing that?
Yeah, so you might have seen it in other talks today as well, but there's a lot of techniques. We use quite extensively knowledge distillation, where we use a powerful large model to train a smaller model to do similar sort of predictions. One of the points I do want to make as well is that there is always a bit of a trade-off and a bit of an art in, you know, what can you afford to give up in a large model? Because you should always generally expect the more inferencing power you have, the more computation you have, the better the performance. And this is the art of reducing the model size. So you make this trade-off and you quantize the dynamic range of the weights. So you gain performance there. You can reduce the number of weights with pruning or sparsity. And we've seen in some other talks, you know, if you have sparse matrix multiplications, that can be done efficiently depending on the hardware. And again, if you look at the hardware you want to deploy to, you might even be constrained to a quantized representation. So like this Sentient chip we're using, I think that uses, you know, 8-bit by default. We've looked at other chips where, you know, NPUs and things, they only have an internal representation that's a limited number of bits. So you can train your model floating point. You have all that performance, but you're forced to quantize down anyway for some particular edge hardware. So yeah, quantization is the other big thing that's very important.
So we see voice as a natural interface for the user, and one's voice can provide context, as I said earlier, for foundational models and GenAI. And MyVoice has a number of patents published around architecture and feature extraction. So we're now going to share how we extract metadata from someone's voice. So perhaps, Tom, you can guide us through that process.
Yeah, I suppose high level, you want to think of this process as taking some acoustic features, something that exists first in the acoustic domain, you capture it, and you represent it internally as a sort of time frequency representation. But you'll have, in software, these acoustic features. And we want to move from that to some other embedding space or some other latent representation space where you might be representing who the speaker is or other characteristics, speaker gender or emotional state, for example. Is someone saying something when they're happy or not? If we go to the next slide, Rick, I think we can sort of give a high level of sort of what's going on there. I mean, at the basic level, yeah, it's, you have some neural network, usually with a convolutional front end, various layers of this, various setups of this, and using sort of pooling layers again, you can do things like take any length of input. So you might, if you have 3 seconds of speech or 10 seconds of speech, you could end up with a fixed dimension vector to represent who that speaker is. But yeah, you go from sort of usually acoustic features through some internal representation, through some sort of dimensionality reduction or time pooling to a fixed dimensional output.
And these voice print vectors you create, are you able to recreate someone's voice from that? Because we talk a lot about security and privacy. Tell us a bit more about how it's secure.
Yeah, so exactly. So you end up with something like a string of 192 numbers, let's say, and you can't go back and get someone's voice from that. So it's a sort of, it's a just representing, it's sort of almost like a hash function for someone's voice, but you don't have the access to the original acoustic data. So when you start to do things like sending that vector to the cloud to say, who it is, I think people can feel a lot more comfortable, about this sort of short string of numbers, not their acoustic features.
And with our current deployment of NanoVoice, obviously the voice print is stored on device as a 1 kilobyte file, and you can have multiple files depending on the number of users and the application. So how do we ensure the information is representative of the user and you have enough data to make an inference? Is it based on multiple samples of audio?
Yeah, so typically you sort of want to be able to represent the speaker and not, let's say, the acoustic condition, or if someone speaks with a cold or they, their voice changes slightly. So we have a sort of intelligent clustering thing where, given multiple samples of speech, we come up with a sort of core representative feature vector for a particular user, and that's just with some sort of intelligent clustering, based around multiple samples, basically.
Brilliant. So when it comes to the voice analysis, from the voice analysis that Tom's mentioned, we get quite a lot of extensive metadata, and that can actually, alongside being used for security, it can actually be used as an input into GenAI to power more context-driven, intuitive and personalized experiences on device. So one application is using the metadata to improve natural language understanding and conversational capabilities of these features and applications, because by analyzing not only the content and also but the characteristics of the user, we can get a better interpretation of their intent, their emotions, the context leading, as a result, leading to more meaningful and engaging interactions. So with voice analysis, we can really deliver two-way conversational AI compared to LLMs with a text input. We also can use voice metadata to provide more personalized interactions. By recognizing the unique voice patterns of the individuals, these systems can tailor responses, recommendations, and services based on the user's preference and traits. And one of these applications we're currently exploring is in the TV streaming space, where we give personalization at a user level within a household. And one further application, although there are many more, can be the use of voice biometrics and GenAI to create adaptive learning environments by providing feedback to the user, whether they're in the workplace or a educational setting. With the data from one's voice and interaction, and the interactions that they're having, we can provide feedback on a personal level and adapt learning materials and strategies to help them improve really in any situation, whether that's in the workplace or at school. Of course, if you'd like to, that's all for our session today, but if you'd like to learn more, we're happy to answer any questions you have. And we'll also be exhibiting on the tinyML Pavilion at Embedded World between the 9th to the 11th of April in a couple of weeks' time.
A big thank you again to all of our sponsors that make this possible. In particular, thank you to the executive strategic partners of tinyML, Qualcomm AI, advancing AI research to make efficient AI ubiquitous, also Sentient, making edge AI a reality, the platinum strategic partners, EmbedUR, Sony AI, deploy vision AI at the edge at scale, the gold strategic partners, ARM, Edge Impulse, Infineon, Renesas, ST Micro, and Synaptics, and the silver strategic partners, which we have here, AIZip, Arduino, BrainChip, Befficient, Greenwaves, Gravity, Hymax, Imagimob, Initera, Noda AI, NXP, Procter & Gamble, Schneider Electric, SensiML, Silicon Labs, and TDK. So that concludes our first day. Don't forget, we have a lot more action-packed agenda for tomorrow as well, starting at the same time. So that concludes our session for today. And thank you for joining, everyone. See you tomorrow.